Shifting focus just a little bit here, a chain lying on the ground is 10 meters long and its mass is 80 kilograms. The question is how much work is required to raise one end of the chain to a height of 6 meters. It's a little bit challenging to draw a dynamic situation in still pictures, but I've given it a shot here. We have the chain lying on the ground, 10 meters long, and then it's starting to be lifted up, and at some point it ends up with one end at a height of 6 meters, the rest is still lying on the ground. For this middle picture, we don't know how much of the chain is being raised, let's say. Well, we'll just call it X meters. Now we're told that this chain has a mass of 80 kilograms and that it's 10 meters long. So each meter has a mass of 80 divided by 10, or 8 kilograms. Or we could say like the mass density is 8 kilograms per meter. Therefore, we can talk about how much mass this length of chain has. This length of chain has 8 kilograms per meter times X meters. That's the mass of the length of chain that's being supported right here. Here's the thing. As we go from the first picture to the second picture, X is increasing. And then we go from the second to the third, X is increasing. The amount of weight that I'm supporting is going to increase as I'm supporting more of the chain. Now I just said weight, we've been talking about mass. Remember that in the metric system, if I need to use weight, I'm going to multiply mass by 9.8 because weight is mass times gravity. That's just because force is equal to ma, and in the case of weight, weight is equal to m times g. Alright, let's get rid of that. So, the weight of this is 78.4 x. As I go from the second picture to the third picture, right? So x meters is how much of the chain I'm holding, and then 6 meters is the amount of chain I'm holding. I have to go an incremental distance from, say, here to there. Guess what that is? Delta x. So, the incremental work done in moving or lifting the chain this infinitesimally small distance is 78.4x delta x. We got an infinite number of those little increments. That's going to lead us to an integral. The work done is going to be an integral. We'll deal with the limits in just a minute. 78.4x dx. At the start of this, none of the chain is being supported, so 0. At the end of it, 6 meters of the chain is being supported, and so this is an integral from 0 to 6. And guess what? This is the same integral that we've been looking at for springs. From A to B, f of x dx. In the case of springs, f of x is equal to kx, where k is a spring constant. Guess what? In the case of this chain, this is really kx. It's no different at all. At all. And it should make perfect sense. The more I stretch a spring, the harder it is to stretch it. The more of this chain I hold up, the harder it is to lift it. As before, the actual calculus of this is pretty straightforward. We'll use the power rule. We got 39.2x squared evaluated from 0 to 6, giving us a result of 1,100, excuse me, I misread that, 1,411.2. What do you mean you misread? I used a calculator, of course. And because this is metric, we're in joules. In general, we can say that the work required to stretch or compress a spring or to lift a heavy chain, rope, cable, that's the kind of thing you'll see in these problems, is W is equal to the integral from A to B of kx dx, where kx is a variable force and dx represents the incremental distance delta x, but of course in the integral, once we take a limit, we write that as dx.